Hello again. Let's see if we can make any sense of coalgebras and final coalgebras in Agda. So let's just focus on streams for now, because these are a good example and it makes things a little bit easier to think of something concrete. So the idea here is that I want to represent an infinite stream of elements of some type A. Right? So compared to a list, I'm never going to stop. So the list, because it's an inductive definition, it's given by an initial algebra. We know that after a finite number of constants, there's always going to be an empty list following it, right? But here, the stream just keeps going forever. So we define this as a record type, because this fits quite well with this idea of observing things, right? So here, I can observe the fields on my record type. So I can observe that there's a head of my stream, which should be an element of A, and there should be a tail of my stream, which should be another stream. Right? This is a recursive definition of a record type. Right? So I have to say that it's co-inductive to get the right meaning of this. I could also say that it's inductive, and then Agda would let me define things differently. So this would mean that I have to stop after a finite number of elements, which I can't here. So there's not actually going to be any inductive streams like this. But the co-inductive ones, we are free to continue forever. Okay, so let's see that this really is a coalgebra. And I'm claiming that this shows this. So to make it a little bit clearer, I'm going to define a functor from set to set. I have to do this with A as a parameter. So take that like that. So I take an argument x, and then I want this to be the functor applied to stream of A. So it's going to be A times x. Right, because now if I plug in stream of A here, I get this thing. Right. So another way to say this is to say that this is f of stream of A. Right. So now we see that it's a coalgebra for this functor f, because we go from a stream of A to f of stream of A. Right. Let's turn this back so it makes it a bit clearer what's going on. Okay, so let's see if we can define this. So we are given a stream, and we have to produce this observation of it. So we should get an element and another stream. And the idea is that this element here should be the head of the stream, and this other stream should be the tail, right? Because this is exactly what I can observe of my stream. So let's do that. Should be something, comma, something. And here I wanted the head of S, A, and here I wanted the tail of S. Okay, so there's not much going on here really, right? We're just observing that we can get this data out of any stream. So it's more interesting to define the unfold function. It says that if I have another coalgebra, so another thing where I can observe the first element and then something else, then I should get the function from y into stream of A. Right. So let's see if we can do this. So I get another coalgebra f, I get a y. Okay, so what can I do? Well, I can apply my function f to this y, right? For y. So that's like observing this y. And this functor is telling me that I'm going to get the first element and a continuation. So if I look at the first projection of this, it's getting me an A. And if I'm looking at the second projection of this, that's getting me a Y. So you could say, okay, let's make a recursive call on this thing. Let's see what Agda says about that. Right, so Agda is not happy about this. Termination checking failed. And why is that? It's because we're not ever getting any information out of this definition, right? This is almost like a Brexit equals Brexit definition, where there's no information coming out. We're just doing recursive calls forever. And Agda rightfully says that, well, this is not useful. but we said that because this stream is infinite, we're not really interested in termination, right? We're just interested in seeing enough data from the stream as we go along. So we really want this function to be what's called productive rather than terminating. It's not going to terminate because this is an infinite object. So we're never going to produce the whole stream. The point is that we should be able to produce enough of the stream as we go along. So that means that before we do a recursive call, we have to expose at least one element from the stream. And a good way to do that is to use co-patterns. So this is why they were originally invented. So instead of trying to do something immediately, I'm going to split on the result. And that means I have to say what the head of the stream is and what the tail of the stream is. So the head is not quite simple, I think. So f of y gave me this pair, and I take the first projection. Because this is like what f thinks the head of y is, whatever this kind of thing is, right? So this is the element that we can expose. And similarly, if I do the second projection, that gets me a y. And now I could try to do a recursive call again. And you could say, well, that's silly, it didn't work before. But now it does work. And why is that? It's because we're now saying what the tail of this thing is, right? So we're not spinning forever, just unfolding and unfolding. We know that we only have to do this recursive call if someone asks us for the tail. So that's why we are productive. We are actually made progress describing more of this stream, because now we're describing what the tail is in terms of this recursive call. So notice that the recursive call itself is not on a smaller thing, right? We're not doing termination checking. We're not going down to a base case to finish. We're in infinite land now. But we are productive because we are saying what the tail is before we do the recursive call. So if you do this by co-pattern matching, it's almost automatic, right? So we're going to see some examples of how to use these things in the next video.